Hello, differential equations students. I'm showing you what might be our last major idea of the semester. If you look at the pretty pictures in chapter 8, they have these things called web diagrams. You can do them yourself. If you got a graphing calculator, which I believe you do, you go into mode and choose sequence. See it? Choose sequence. And then when you got that chosen, go up to format and choose web. You can do time series, but it'll just be a bunch of dots. You want web, okay? Then watch what happens. You go to y equals in sequence, and you have this very weird looking interface. You've never seen anything like this. Now to enter what I have there, I have to use a U, and it's not the alphanumeric U, it's this U. Do you see that? That's the U that you use to match that U right there. Those U's match. Same thing, a funny thing happens. See this button here? See this button here? X for function mode, T for parametric, theta for polar, N for sequential mode, and you get this funny little italic N when you press it. This U of N minus 1 actually stands for U sub N minus 1. This U of N stands for U sub N. It's time series. It's difference equations, kids. It's the same stuff we've been doing, only you get a graphical look at what's going on. And let's take a look at this thing. Here's the starting point is going to be at 0.7. And when I hit graph, you're going to see the curve. If you did 3x times 1 minus x, you'd get a parabola facing down. You see that curve, and then they show you the line y equals x. So here's the curve that we entered in the u equals. That's the curve. But this is the line. I guess if this is the initial value, this is the input, and this is the output. This is the input equals the output. And what you do is you hit trace. See trace? You get this little butterfly, and then you use this right-hand arrow. Check it out. It goes up here. It goes to the next thing. It goes to this. It goes to this. It goes to this. Let me just tell you what the calculator just did for me. It took 0.7, which was my set starting point. It calculated it on the curve, took that y coordinate on the curve, and then made it the x and y coordinate the same, and then used the new x coordinate as the y coordinate. And a funny thing happened. The new y coordinate got me back to here, which was the old x coordinate. This is called a loop. You can see it. It's just a loop. If I keep going around, sorry, I got to start with trace again. It just keeps going around. I just keep getting those values back. Can you see them down below? All right, let's try another starting point. What if I start with, say, 0.5? And I hit graph. Can you see it okay? All right. There's a little bit of yuts on my calculator screen there. All right, I'm hitting trace. I go up. And this is not making a loop. It's kind of zooming in on that center point. This is called a spiral. My values are spiraling in on this value, and that value happens to be 2/3. So you can get really pretty pictures from these things, but this guy is a spiral. The thing we saw before was a loop. You can see this is kind of like a loop, but it isn't, because I keep getting different values, and the values keep zooming in on that. Like if I sat here and did this all day, it would get closer and closer to the 2/3 mark. All right, let's try another starting point. How about if I start with point? Oh, I already had the point. 1, 2, 7, 3, 2, 2. All right, let's see what happens. I hit graph. So this is x equals 1, so I'm starting over here somewhere. Let's see it. There's a little butterfly. You can see the starting location numbers. And I'm pressing the arrows to do the math here. So do you see in this, whenever I come back to this line, the x and y coordinates are the same. And I go back to the curve, and it goes right to the fixed point, 2/3. This is called a sink. So this value started here and went to the fixed point. So that's a sink. Now watch what happens if I try something close to 0.127322, but isn't 127322. How about if I go to just 1.4? Let's just clear it and make it 0.14. That's close. That's a close starting point. Let's see what happens. So trace, move it, doot, 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 doot. Oh, it's not a sync. Looks like we got a loop. Isn't that weird? I got a starting point that was really close to my original starting place, and I didn't get a sync. I got a loop. Now, this is the butterfly effect, ladies and gentlemen, because there was a very small change from 0.127 to 0.14, a very small change in input, but the long-term behavior is completely different. A sync, you hit that fixed point and you stay there the rest of your life. A loop, you just keep saying two values back and forth. You get repeated values. So you got to understand this idea because it's behind a lot of things. We saw this with the weather thing when we did the Lorenz knots. A small change in input can have a big change in long term. And here's an example of it that you can do on your calculator. So it's related to the weather. It's related to anything with chaos. And that's why it's in a chapter that has dynamical systems in the title. This is a dynamical system. There's some change in value, and a small change in value leading to different long-term behavior. That's butterfly effect. And what's actually true is, depending on what your curve is and what your inputs are, there isn't a set way to know what's going to happen. So math people think this is like catnip. This is like magic to them. How do you do these things? How do you decide? So what do you need to be able to do for a grade on this stuff? Well, you have to be able to tell a loop from a sync, from a spiral. You have to be able to tell how, for small changes in input, if you get different output behavior, different long-term behavior, that's an example of the butterfly effect, because the flapping of a butterfly's wing next to the wind sensor would have been a very small change, but it can have a large change in output behavior when you have a complicated system like this. And it isn't that complicated. I mean, it looks complicated to you because you've never seen it before, but that's just 3x times 1 minus x. It's not a fancy thing. The curve's just an upside down parabola. It's not that big a deal. But you get these things. Well, let's change this to something else. Let's make it how about 0.34. Let's just see what we get. So you can play with this stuff. Isn't this fun? Graph, trace, and then the right arrow. Oh, this guy's like a sync, but he's making a very small little looks like it could be a spiral. Really funny how it's almost a sync. It's so close to being a sync, it's funny. Now here's another thing you can do. Change that 3. Change it to a, let's change it to a 2.8. You'd think, well, that's not going to be that much different, right? It looks about the same. And let's take a value that gave us the loop. How about if I start with, or the one that I just did is already in there. Let's hit trace. And I'm getting the same kind of behavior. I'm going to try that 0.7 and see what happens. Trace, boop, 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 boop. Now this is a value that when I had a 3 parked here, I got a loop. Now you can see I'm getting a spiral. I'm getting a really kind of pretty spiral with this one. So that's another thing that the math people are very turned on about. It's a pretty diagram there. Isn't that pretty? And you could print that up and put it on a badge. It's kind of cool. But you can you can tweak this system and get different things going for it. And there's no set way to know what's going to happen ahead of time. So it's an area of research people actually get paid to study this stuff. Isn't it amazing? All right, so be able to tell a loop from a spiral, from a sync. This one is a spiral. Talk to you later.